Guys, so today we're going to move on and we are going to look at things that we call intermolecular forces. So I'm just using the shorthand IMF, and there are three of them, and we're going to hopefully be able to give you some hints that will help you work out which of the three intermolecular forces are present in a sample of a compound. We're going to still be using our electronegativity values to work out are there polar bonds present, and we'll also be looking to see can we figure out is our molecule polar or non-polar. So the first thing we're going to start with is intramolecular forces, and these are essentially forces between atoms within a molecule. So it's essentially the type of bonding that's present, so whether something is ionic or covalent. And just in terms of strength of ionic and covalent bonds, well, they need a huge amount of energy to break them. They're very, very stable, so it's not going to be easy to break ionic or covalent bonds. The part that we're really focused on today is the thing called intermolecular forces. So what these are, they're forces of attractions, but now they're between different molecules. So you have a version of this diagram in your book. So this is the the covalent bond, putting in my lone pairs, and there is going to be a force of attraction between water molecules, and these are the intermolecular forces. So they are generally weak in terms of you don't need as much energy to disrupt them, and they will determine the physical properties of your substance. So things like whether or not something is a solid, a liquid, or a gas, its melting point, its boiling point, even its density. So it is the forces between your molecules, they are going to determine what their physical properties are going to be. So we have three intermolecular forces that we're interested in. The first one is the Van der Waals forces, and if you can get into your head that this has what's called a temporary dipole. So we've seen dipoles when we were doing our electronegativity for a particular bond. So we know that this is a negative and this is a positive, so that is a dipole. We're going to, and I'm putting these descriptors in front of them. So of the three intermolecular forces, the Van der Waals is the weakest. We then have dipole-dipole interactions, which we'll get into next lesson, and these are stronger again. And finally, we have hydrogen bonding, which is the strongest of the three intermolecular forces. We talked about permanent dipoles on page 153, so if you want to go back and have a read and have a look. But this is a permanent dipole because it is always going to be present once the electronegativity is between greater than 0.4 and less than 1.7. Okay, and again, we're putting these descriptors in front of them to answer any version of a question that the SEC might answer. So always include them before each of the intermolecular forces. So I am going to, for the most part of this, I'm going to show you a little movie clip first, and let's see where we go. So this is our atom, and what you're seeing, the little bulges, are the electrons moving in their orbitals. So they're changing position, and once they change position, then you're going to have a different distribution of positive and negative charges in your little atom. So they're putting up the little delta positive and the little delta negatives. And if that's happening in one atom, then it's going to affect the atom next to it. So they're the dipole, temporary dipole, the delta positives and delta negative are changing all of the time. And when you put two atoms next to each other, well, if one part of the left one is delta negative, then it's going to push the electrons to the other side on the right hand side one. And that is what the Van der Waals force is. So it is a temporary dipole that's happening because your electrons are moving. Okay, so that these little lines here that are drawing are showing you kind of the little bits of forces of attraction that are happening between your atoms in this diagram because the electrons are moving. So they'll attract different parts as the electrons change their position all of the time. So if I wanted to turn, we'll presume this is a liquid, if I want to turn that into a gas, then I have to put in energy that's going to be greater than the van der Waals to turn that into a gas. Okay, so if you're a small molecule, you'll have small dipoles present, so your van der Waals will be relatively low. Once you start getting bigger, you have more electrons, you can make bigger dipoles. So once you have bigger van der Waals forces, you will have bigger interactions between your molecules or your atoms, so you'll get an increase in your boiling point. So the bigger the molecule, the higher the molecular mass, the more electrons it has, the more van der Waals, and therefore the higher the melting and the boiling points. So this is an organic compound. It is called pentane, so it has a molar mass of 72. It's going to have a lot of van der Waals, and you need to increase your temperatures to 36 degrees to turn that from a liquid into a gas. Same molecular mass. Here, slightly different arrangement in terms of the formula, but because there's a different arrangement, you're now going to have smaller van der Waals and you will have lower melting point or boiling point. Okay, I'm going to leave that there. Come back to this. Okay, so the first rule, and you need to write this in where it says your weakest van der Waals forces being the number 1. So we're putting weakest in here, and you're going to keep that descriptor. And just next to it, you're going to write and you're going to highlight every atom or every molecule that you come across has van der Waals. Okay, it's a prerequisite because they all have electrons, so therefore they're going to have it. And when we look at different molecules, you just need to decide, is it only van der Waals or is there another intermolecular force present? So they'll be the type of things you're asking yourself. So for your notes, these are caused by temporary dipoles produced by the random movement of electrons, and it is of electrons around the nucleus. So again, they are much weaker than ionic and covalent bonds. So therefore, you just have to input a small amount of energy usually to disrupt them. Now, I'm just going to go through the next few slides. There's nothing to write down just yet, but we'll just see can we explain it again. So this is our helium, and this is showing us the fact that we have now electrons at either side. Helium has 2 electrons in its outer shell. There's an even distribution of charge. There is no delta positive or delta negative, but because our electrons are moving in their orbitals, I now have my 2 electrons over here, and because of that, we now end up making a temporary dipole. So over here now will be slightly more negative, and over on the left-hand side, it's slightly more positive. And then in the next instance, because the electrons have moved, so too does the dipole. So my electrons are now over here, so this little portion is delta negative, and that's going to keep on changing as the electrons move around. So it is very unlikely that the charges will be perfectly balanced. So there's always going to be some part of the molecule that is, or atom, that is delta negative, and another part that is going to be delta positive. And this is not even split second. This is happening so fast over time. So the fact that I'm getting this little partial positive negative and this little partial positive for one moment in time makes what's called a temporary dipole. because the position is changing all of the time. So now we go to a bigger atom. So the bigger the atom, the more electrons it has, it's going to have more of this weakest van der Waals forces. So this is with your even distribution on the left hand side, but as we've said, our electrons are all moving in their s and p orbitals. So we now make one portion delta positive and another portion delta negative. And because there are more electrons involved, you're getting a much bigger temporary dipole. So this moment in time, the atoms have no temporary dipoles. They're not attracted to each other. They'd have a really, really low melting point or boiling point if you needed to input energy to make them change state. But if we get the movement of the electrons, we'll get the temporary dipoles formed, and this will cause another temporary dipole to form in the other atom or molecule. So obviously negative would be attracted to positive. So the fact that you get a temporary dipole in one atom or one molecule, it's going to influence the others that are around them. And once they're attracted to each other in some way, I now need to put energy in here to disrupt that attraction if I want to change its state or find its melting or boiling point. So once there's interaction between your molecules or your atoms, they're going to have higher melting points and boiling points. Now you have a schematic like this in your book on page 163 in mine, so we'll just see, can we label it up? Now you're never going to have to produce this. I'll tell you in a second what you will have to produce. So over here, this is just a normal atom. You can ignore this, you don't have it in yours. The electrons are perfectly balanced with the positive charge in the nucleus, and if it will form a temporary dipole down here because you're getting movement of electrons. So over here is going to be my delta negative, and over here will be my delta positive side. Okay, so we can just put this like this. Now, once you have a second molecule or second atom that is going to come into play, then this is my second atom here. This is my first here. And we put in our delta positive here and our delta negative here. And once that second atom or molecule comes near the first one, it's going to form a little dipole itself, and it will be opposite because these guys now are going to be attracted to each other. So that is the intermolecular force. So this next part may not be quite the same as it is in yours, but what do you need to be able to do? So you need to be to determine whether the weakest van der Waals is the only IMF force that's present. So the rule that I want you to get into your head is everything has weakest van der Waals forces, and it's because everything has electrons. And if you have to determine which molecule has the greatest van der Waals, well then you're looking at this. You're looking at the higher the molecular mass of the atom, the more electrons will be present, and then that'll be the bigger the weakest van der Waals forces are between atoms. So we've already done scenarios where we had to calculate molar mass. So I'm not going to use HCl, I'm going to use CH4. So this is where we looked at our mass number, and carbon is 12. We look at hydrogen, and the mass number of hydrogen is 1 by 4. So that gives us a molar mass of 16. And if we're then comparing that to something like O2, well, oxygen is going to be 16 by 2 for its mass number. It's going to be 32. So when I look at these, oxygen has a bigger van der Waals because it has a bigger molar mass. Okay, so if I was to look up the boiling point of methane versus oxygen, I would see that oxygen will have the much higher boiling point. So that is what everything on this slide means. So everything has weaker van der Waals, and to determine how much it has, you calculate the molar mass, and therefore you figure out which has the bigger van der Waals. Okay, so the end of this says bigger, weaker van der Waals means a higher melting and a higher boiling point. Okay, so what you're going to do for me now, it's on page 164 in mine. You are going to calculate their molar masses by adding up their mass numbers. So when you look at your periodic table, if we take carbon, depending on your version, the atomic number is always the smaller number. So this is your atomic, and your mass number is always the bigger number, and it's the mass numbers that you're going to be using to work out the molar mass, and then you should be able to put these guys into order of who has the most van der Waals. So you're going to go from lowest to highest, or least to most van der Waals in this. Once you have done that, just at the end, to maybe before you do that, to help you, so the effect of temporary dipoles, if there are no temporary dipoles, there's no attraction between your molecules. Now the reality is this never happens because the electrons are always moving, but if it did, then the boiling point and melting point would be exceptionally low, like we're talking in the negative hundreds. But if there are temporary dipoles, there are attraction between molecules, and therefore you need more energy to disrupt these weakest van der Waals forces between your molecules, and so the boiling points and melting points will increase as the molar mass gets bigger. So that's going to go on the bottom of page 164, or underneath that table. Then here you're just going to have a look. So you are going to, we have to kind of subdivide the things now. So you are going to have a look at these molecules, and you're going to have to decide here, so if you want to write it over here, are they polar or non-polar molecules? So this is using your rules. So you're going to decide, is it polar or non-polar, and I want you to tell me which non-polar molecule has the highest boiling point and which has the lowest boiling point. And I'm going to help you out and say in this list there are 2 polar molecules present. So you just disregard the polar molecules and you look at the remaining ones and you decide which one would have the highest boiling point and which one would have the lowest boiling point, and it's using the order from above and the molar masses. And this last bit then, you should be able to do it. So I want you to look at the graph and state what happens to the boiling point with increased number of electrons. That's your state, and then explain. So all of these molecules here only have weaker van der Waals. So can you explain why whatever trend you're getting is the way it is from the things we have done today? I think there are 2 very short exam questions for you to do as well in the class notebook page, and I am on Zoom if you need me.